Following the motto, prepare for trouble and make it double, Apple not only announced one, but two new SoCs at yesterday's Unleashed event, the M1 Pro and the M1 Max. Compared to all previous Apple Silicon, these new chips are monsters in almost every metric, performance and efficiency, but also transistor count and die size. In this video, I will first talk about performance before analyzing the silicon itself. We will compare transistor count to the competition, look at where Apple focused their engineering on, and talk about the general design philosophy behind the new M1 family. But let's start with the specs first. The original M1, which Apple released about a year ago, is a 8-core CPU design with 4 high-performance cores that share 12 megabytes of L2 cache and 4 high-efficiency cores that share 4 megabytes of L2 cache. The GPU consists of 8 shader cores and shares 8 megabytes of system-level cache with the 16-core neural engine. The memory setup uses up to 16 gigabytes of low-power DDR4 2466 memory on a 128-bit wide bus, which results in 68 gigabytes of bandwidth. When it comes to the CPU design, both the new M1 Pro and the M1 Max offer the same setup. Up to 8 high-performance cores with 24 megabytes of L2 cache and 2 high-efficiency cores with 4 megabytes of L2 cache. There are 2 interesting things to note here. First, the high-performance cores are basically just a doubled M1 setup, not unlike AMD's CCX approach. It seems like Apple is using 2 clusters with each 4 cores and 12 megabytes of L2 cache instead of redesigning a new 8-core cluster from scratch. Second, the high-efficiency cores are cut in half, from 4 in the base M1 down to 2 in the M1 Pro and Max. This is a really interesting decision in my opinion, since the efficiency cores use very little die space and the L2 cache stays the same at 4 megabytes. From my point of view, it would have been great for consistency purposes to offer the same amount of efficiency cores across all chips of the M1 family. I'm sure Apple made a conscious decision here, and I would love to know why they did that. It's also fun to see that when it comes to designing high-performance chips, Apple is cutting back on the big.LITTLE hybrid approach. Yes, the M1 Pro and Max still offer performance and efficiency cores, but with 8 big and only 2 little cores, Apple is clearly focusing on their big core design to deliver their performance to their Pro customers. Plus, we're still talking about laptops, where efficiency cores come in handy for battery life. Just last week, AMD talked about their future and said that a hybrid approach isn't anything that's close on their roadmap. Intel, on the other hand, will introduce their new Alder Lake CPUs in just about 2 weeks' time, and they will combine 8 big and 8 little cores for a desktop CPU. Intel CEO Pat Gelsinger mentioned how he wants to win back Apple with superior design. It seems to me that Apple and Intel have a completely different understanding on how and when to use big and little cores to offer the best amount of performance. The GPU design is where the M1 Pro and the M1 Max starts to show their differences. With 16 GPU cores, the M1 Pro doubles up the original M1, and with a whopping 32 GPU cores, the M1 Max doubles that again. That's 4 times the amount of cores as compared to the base M1 version. Apple didn't give us numbers for the system-level cache, but the M1 Pro seems to have 2 blocks and the M1 Max offers 4 blocks. I don't know if these blocks hold 8 or 60 megabytes of cache each, and that would affect how much cache the Pro and the Max chip have. If it's 8 megabytes, the Pro would offer 60 megabytes of cache and the Max 32, and if it's 60 megabytes, the Pro would offer 32 megabytes and the Max would offer 64 megabytes of system-level cache. According to Apple, the neural engine in the Pro and Max chips will stick with the same 16-core engine as in the base M1. Interestingly, when looking at the die shots, it almost looks like the M1 Max has 2 neural engines, but that might also be my mistake. The memory setup also differs between the Pro and the Max. Both SoCs use low-power DDR5 6400 memory, but the Pro version of the chip has a 256-bit wide memory interface resulting in about 200 gigabytes per second of bandwidth, and the Max version has a 512-bit wide interface resulting in about 400 gigabytes per second of bandwidth. If you watch my videos, you already know that CPUs are usually more keen on latency and GPUs usually like bandwidth more. A large memory interface coupled with low-power DDR5 can offer the best of both worlds, offering low latency for the CPU and high bandwidth for the GPU. Especially the M1 Max with its 400 GB per second of bandwidth is really impressive if you compare it to a dedicated GPU like the RTX 3070, for example, which offers 448 GB per second of bandwidth. That's all the base stats for the new chips, so let's talk about performance. The good news is that Apple gave us some hard numbers this time, unlike with the A15 Bionic launch in September. Compared to the base M1, the M1 Pro and Max both offer 70% more CPU performance. When it comes to GPU performance, the M1 Pro is twice as fast as the M1, and the M1 Max is 4 times as fast as the M1. These are some really impressive numbers, but they also imply that the performance uplift is entirely due to the increase in CPU and GPU cores and not based on architectural changes. Apple kept the M1 name for a reason. All 3 chips are part of the same family, they only use different amount of silicon. Doubling the performance cores, but cutting the efficiency cores by 50% gives you around 70% more CPU performance, just like Apple claims. And that the M1 Pro with 2 times the GPU cores offers 2 times the GPU performance, and the M1 Max with 4 times the GPU cores offers 4 times the GPU performance isn't surprising either. The M1 offers 2.6 teraflops, the M1 Pro 5.2 teraflops, and the M1 Max 10.4 teraflops. That means that the clock speed stays the same across all of these 3 chips. Of course, you can't simply scale the GPU cores alone, you also have to scale the rest of the system with it. A M1 Max with the same 8MB of system level cache and only 68GB of memory bandwidth wouldn't be able to offer 4 times the performance. But since Apple scaled all the related parts, these performance numbers do make a lot of sense. Another interesting comparison would be the custom AMD APU for the PlayStation 5. It offers 8 Zen 2 CPU cores, a 10.3 teraflop RDNA 2-based GPU, and 448GB of bandwidth. That sounds quite similar to the M1 Max with its 8 high-performance cores, 10.4 teraflops of GPU power, and 400GB of bandwidth. Now that we know how these chips perform, what about the size of them? Apple was nice enough to give us a couple of inputs. We have die shots and transistor counts, and on top of that, all 3 M1 chips are based on the same TSMC 5nm process node. The base M1 has 16 billion transistors and a die size of around 120mm squared. If we scale these numbers, the M1 Pro with its 33.7 billion transistors should be around 250mm squared, and the M1 Max with its 57 billion transistors should be approximately 430mm squared. That's a lot of transistors and pretty huge die sizes too, especially if you consider that Apple is using TSMC's bleeding edge 5nm process. Apple does have the advantage when it comes to transistor density, but their chips still turn out to be massive. To give you an example of how many transistors they use, a Ryzen 9 5950X consists of 2 Zen 3 chiplets using 4.15 billion transistors each and a single I/O die with about 2.1 billion transistors. In total, that's about 10.4 billion transistors for a full Ryzen 9 5950X. A full Navi 21 chip, for example as used in a Radeon RX 6900 XT, has 26.8 billion transistors. That means the combined transistor count of a Ryzen 9 5950X and a RX 6900 XT would be around 37 billion transistors. That's only slightly above the 33.7 billion transistors of the M1 Pro and a whopping 20 billion transistors behind the 57 billion transistors of the M1 Max. Of course, the Apple SoCs pack more than just GPU and CPU cores. There is the neural engine, there are accelerators and other image enhancing chips, but all of this doesn't explain why Apple's chips are so large. The real reason why Apple is creating these monster chips is power efficiency. When it comes to silicon design, there are 2 ways of increasing performance, both with their own strengths and weaknesses. The first approach is to simply raise clock speeds. The positive aspect of this approach is that raising clock speeds isn't transistor intensive. If you simply clock your GPU or CPU higher, you get more performance without actually needing a bigger chip. This saves die space and as a result means better yield and cheaper chips. The drawback of increasing clock speeds is the increase in power consumption. With higher clock speeds, you also have to increase the voltage, and that has a massive impact on power draw. The other way of increasing performance is by implementing a wider design. The drawbacks of this approach is that you need more transistors to increase your CPU and GPU cores, which will result in a larger chip and lower yields and more expensive production cost in general. But on the plus side, the power draw doesn't increase exponentially. Apple could build smaller chips with less cores and just increase the clock speeds, but that would affect their most important asset, their incredible power efficiency. The major advantage of Apple Silicon is that it delivers high performance at low TDP. There are other laptops with fast GPUs and CPUs, but they aren't able to deliver their full performance on battery power alone. As a result, Apple's MacBooks offer something no other company can offer, truly mobile and portable power. And to achieve this, Apple spends a lot on their silicon. Of course, Apple also has to fight with the issues of low yield when you increase the chip size and the limitations of current TSMC process nodes. But there is one solution that everyone else uses and Apple uses too: product segmentation. There are 3 different SKUs for the M1 Pro and 2 different SKUs for the M1 Max, allowing Apple to sell chips that did not pass the full quality checks. The M1 Pro has cut-down versions with 8 CPU cores and 14 GPU cores, or a combination of both. And the M1 Max is also available with a cut-down 24 GPU core version. I still wonder what happens to M1 Max chips that have like one defective CPU core. It would be a shame to throw them away. I think Apple's approach to spend a lot on silicon to offer best-in-class power efficiency is already paying off. No one really wants the old Intel-based Macs back, and I'm sure Apple also increased their margins too. Leave a comment down below and tell me what you think about Apple's approach. As always, if you enjoyed this video, please leave a like, follow for more content, and see you next time.